Welcome back. The next part of probability we're going to talk about is binomial experiments. Okay, binomial experiments are experiments that consist of a fixed number of trials with the following features. Okay, each trial has two possible outcomes, one of which is denoted as success. So an example of this might be flipping a coin, because the two possible outcomes are heads or tails, and we're going to say that heads is the success. Okay. The next qualifier is that the results of the trial are independent events. Like how I flipped that first coin has no bearing on how I flipped that second coin. And then the third qualifier is the probability of success is the same for every trial. Okay? And it doesn't have to be a 50-50, heads 50, tails 50. It could be like 20-80 or 40-60, but it just needs to be that same probability every single time. Okay? So, going back to the first one, actually, let me explain a little more. So it doesn't even just have to be something with two outcomes. It just has to be something with what we call two possible outcomes. So I could also say like my experiment could be rolling a die and getting a number greater than 2. Okay, because one outcome is less than 2 and one outcome is greater than 2. Okay, and so that's where I'm not going to get the 50-50 odds. All right, moving along. Is it a binomial experiment? So the first thing is recognizing these experiments. So example 1 is, in a class of 23 students, 7 students completed the term project. 2 students selected at random have to give presentations. Success is that the student has completed the project. So the question is this a binomial experiment? Okay, so there's 2 possible outcomes. That part is very true. Okay, one is that they completed the experiment, that's success, and one is that they did not complete the experiment, or no success. Okay, now the results of the trial are independent events. See, this is where we run into a problem, along with the probability of success is the same for every trial. Because if we were to give the odds of the situation, the first student we grab, there's the odds 7 out of 23 that the one I randomly choose is going to have completed the project. Success, yay. The problem is that the second student's odds would only be 6 out of 22 because I've removed one student from the class who did complete it, so now there's only 6 left and there's only 22 students left. And so because these are not the same and they're not independent events, this is not a binomial distribution, and then we couldn't use the formulas that follow. So just keep that in mind as we're doing this, okay? All right, so if it is a binomial distribution, we use what we call the binomial probability formula. There's only 3 things you need to be able to know to plug into that. The first thing is n, which is the number of trials. P is the probability of success for each trial, and then r is the number of successes. And then you'll see, here's our formula. So we have the probability of some number of successes is equal to the number of trials with the combination at the, anyway, this P is this P, okay? So let's just go through an example. A grocery store gives away scratch-off cards with a purchase of more than $100. Terrell has 5 scratch-off cards that he's gotten from these endeavors. What's the probability that he has exactly 3 winning cards if each card has a 30% chance of being a winner? So with scratch-offs, whether I win or lose on one has no effect on the probability of a next. So that satisfies this whole, they're independent events. Each trial has 2 possible outcomes. I can either win or I cannot win with these scratch-offs. And the probability is 30% every time. Okay, so this is a binomial experiment. So we can use this formula then to solve it because it does satisfy all the binomial experiment conditions. So we can go ahead and start by defining the variables for the formula. When I read this, I say he has 5 scratch-off cards. That's our number of trials, n equals 5. The probability that he wins is 30%. So we change that to a decimal, move that decimal 2 times, 0.3. And then the r, the number of successes, is in this case exactly 3, so we write 3. Okay? Then we just plug it into that binomial formula I gave you up here. So we're saying the probability of him winning 3 times is equal to, and we plug in the 5 for the n, we have our combinations, we plug in the 3 for the r, we have 0.3 for the p to the r, and then we have 1 minus that point. Anyways, simplify it all down. So this is going to give me 3, this is going to give me 0.7 to the second. You can type it all in at once, do it separately, whatever the case is. I come out with the probability of 3 wins being 0.1323. Now on Delta Math, you just type it in like this. Okay, probability is usually a number between 0 and 1, where 1 is 100% of the time. However, a lot of us think about it in terms of percent, so when I go to explain it, I'm going to say probability of having exactly 3 winning cards is about 13%, because I would move that decimal back over. Okay, that's our simplistic situation. Now, the second part of the delta math is at most or at least the harder binomial distributions. So all that means is that now we have two different situations that we're going to combine. So what I mean by that is, this one says, for the same exact situation, so Terrell, he goes and he gets scratch-off cards, he has 5 scratch-off cards, they have a 30% chance of winning. We want to know, to the nearest tenth of a percent, what's the probability that he has more than 3 winning cards, okay? So here, if he has more than 3, that means he could have 4 or 5 winning cards. So what we're going to do is we're going to find the probability of him having 4 winning cards, the probability of him having 5 winning cards, and then we're just going to add those probabilities. So starting with the 4, still 5 trials, still 30% chance of win, but now the number of successes is 4. For the 5, still 5 trials, still that 30% chance of winning, but now he's winning all 5. Okay, so individually, I plug them into that same formula. And I end up writing my formula like this. I just went ahead and did the 1 minus p and got 0.7. And I went ahead and did the n minus r to get that 1. Okay, evaluate, this is what I get. Do the same thing over here. Now I have 5c5, 0.7 again, but now this is 0. Okay, evaluate. So the probability of 4 wins is 2.8%. Probability of 5 is less than 1%. But I go ahead and I add those two numbers, and that gives me that the probability of him having more than 3 winning cards is 0.03078. I could type that into Desmos. I don't need to turn it into a percent, not for Desmos, for Delta Math. Or if I want to turn it into a percent, because that's how some of us think, it's about 3.1% chance that he'd actually win with 4 or 5, more than 3. Okay? All right, Delta Math practice.